right away. Let's see, is it doing it? Yep. All right, so the first topic and then is sequences. A sequence is a list of numbers, A1, A2, A3, A4. There's just indexed numbers here. And goes on forever. A more formal definition is to say it's a function whose domain is the natural numbers. Remember what the natural numbers are? It's just the numbers 1, 2, 3, 4, 5, 6, and on forever. The counting numbers, we call them. Right? So what I did was you put in 1, you get back A1. Put in 2, you get back A2. You put in 3, you get back A3. So this is like A of 1, A of 2, A of 3 for the function A. That's all a sequence is. It's a function whose domain is the natural numbers. And there's lots of abstract speculations you can get on this. You don't actually have to start with 1 as the index. You can start with 0 or whatever your other favorite number is. Just to lay in abstract a little bit here right in the beginning for fun, we'll say, really, it doesn't matter as long as you pair them up with an infinite list of integers, numbers with nothing after the decimal points. It doesn't matter which one you start at. For instance, if I took the numbers and indexed them A, 0, A1, A2, and put it on forever. This is also an infinite sequence because the idea is I just pair this one with this one, this one with this one, and this one with this one. And when we compare infinite size sets, we say if they can be paired up 1 to 1, then they're the same size. Right? So it doesn't matter if you start them here or start them here. They're still the same size infinite list. Even though this has all the numbers in this, all the indices in this list, plus one more, we still say they're the same length because, suppose you got somebody from a different country or something and their list of objects was squiggle, zot, and flefla, and whatever else. And you wanted to pair them up and say, which is bigger, their list of symbols or ours? Oh, what do? You just pair them 1 to 1, and if they're paired 1 to 1, then they're the same size. It's like you go to a football stadium. You can't count everybody, so everybody sit down. And if there's people still standing, then you say there's more people. If there's seats left, then you say there's more seats. That's what we do with infinite lists of numbers, and that's part of what you pick up coming to class. So I say, come to class. If you don't come in person, at least come online, because you pick up lots of things that help you in your later math courses. I'm amazed how often I had little things I picked up as I went along that I needed when I became a math major later in order to understand what was going on. And so if you understand that these lists of numbers, it doesn't matter where you start, it's still considered the same number of elements in the sequence because you can still pair these off in 1 to 1 fashion, whether you start at 0 or 1 or minus 100 or whatever, or use your own special symbols. As long as you can pair them off 1 to 1, you say they're the same size. We'll have more to say about that as the semester goes on. But that's a little bit of abstract stuff, and you don't need to know that for the test. But here's a list of numbers, for instance. Suppose I put 1/2, 1/4, 1/8, and so on. We'll say there's a list of numbers. And now if these numbers are following a pattern, we can determine a formula for the nth number. So we call in the sequence n, where n is any natural number here, the nth term. So A1 is the first term, A2 is the second term. Part of this course is just learning terminology at this point, all right? And now maybe we want to find a formula for it. What's the formula here? What you do, and I'm not going to make hard problems figuring this out. It's just a matter of being intuitive, and somebody could always make the next number be whatever they want. But if you're supposed to be recognizing a pattern, what's this pattern look like? Well, you think about it. This looks like 1/2 to the 1. What you do is you label these. This is 1, right? Index. This is A1. This is A2. This is A3. And so you label these and say, what would go with 1, 2, 3 here? if you think about it, this is 1 over 2 to the 1, 1 over 2 to the 2, 1 over 2 to the 3, and it looks like that's probably the pattern I mean, right? And so if I think of it that way, I can say the nth term must be 1 over 2 to the n, and then I keep going on forever. And so we'll say an is equal to 1 over 2 to the n is the nth term for this one. There's a couple problems at the beginning just to get you used to this, to say, what is the nth term, or what's a formula for the nth term? That's all you do. You look at it and you put down the numbers 1, 2, 3 and try and figure out how can I index these, like maybe they're powers or products or something like that, and figure out what it is. Once you find the formula, then you can try and do neat calculus things like find the limit of the sequence. If these numbers are settling down to something like this is getting smaller and smaller, it looks like it's settling down to 0, right? If these numbers are getting closer and closer to something, we say that's its limit, just like we did in calculus 1 for continuous functions. These functions of the discrete list, 1, 2, 3, 4, etc., can also be settling down to a fixed number. Pardon me, I have to come over here and periodically move the camera so you can see. Always helps to be able to see in this class. That's all you have online, right? So now we'll say, what is a limit? Anybody remember limits from calculus 1? Calculus 1, boy, I think when I look at that, it's so clever what Newton and Leibniz came up with to be able to make rigorous the concept of a limit. Obviously, those numbers are coming closer and closer to 0, but how do you make that absolutely rigorous? There was a definition in calculus 1 that this will look a lot like, right? If for each number epsilon greater than 0, this is for sequences of real numbers again, there exists a number n such that the difference between some number L that you pick and the nth term is less than epsilon whenever n is bigger than or equal to n, then we say that the limit as n goes to infinity, I'll write n arrow infinity, of this sequence, A1, A2, A3, etc., sound like the king of Siam in this class sometimes, is L. And to denote this, we write the following short notation. Limit n goes to infinity of an equals L, just like that. Very similar to what you did in calculus 1. That looks similar. Sometimes I find classes actually skip this part. When they skip this, they leave a big hole because this doesn't make sense in calculus 3 now. And furthermore, you extend this in calculus 4, so I think it's important to do it. In case you didn't see it or missed class that day or don't remember it for some reason, sometimes that stuff is too abstract. What is this really saying? How is this such a brilliant idea that Newton and Leibniz and later others for other applications came up with? See if I can back this out a little bit. It's similar to calculus 1. All right. What did you see in calculus 1? This was the concept. And again, stop me. This is an easy class to ask questions because there's not very many of you, right? If I want to say the limit of a function is L, and maybe it wobbles around like this, and eventually settles down to this horizontal line, y equals L, how can I prove rigorously, or what's the definition by which I can prove rigorously, that the limit is L of this function y equals f of x, right? Remember that definition? They call it the epsilon delta definition sometimes. This was the definition in calculus 1. it said if for each epsilon greater than 0, yeah, it looks like that, right? There exists, this looks like that so far, but now it changes. It exists a delta greater than 0, a number delta. Such that absolute value of L minus f of x is less than epsilon whenever x minus, absolute value of x minus x0 is less than delta. Then we say, and I'll just write the notation, that the limit as x goes to x0 or x naught of f of x is L. This is from Calculus 1, so I won't ask you this on the test. But does that look familiar? I hope. This was the rigorous definition by which you prove something has a particular limit. Now, why didn't you do this over and over in calculus? It's because what happens is there's a few nice theorems you come up with in Calculus 1 that by which you prove from this definition that if a function has certain properties, then it has certain limits. Like the limit of the sum is the sum of the limits, right? You pull a constant out of limit. You prove that from this definition for each of those theorems, and then you can figure limits very nicely without having to go back to this definition every time. So you didn't use this definition much because you instead proved theorems from this definition and then just used the theorems. But this is in essence what you're proving with those theorems each time. Now, what did this say? It said, if you give me a number epsilon, no matter how small, maybe you're going to make epsilon this small, I'll make an interval of width 2 epsilon. L plus epsilon will be this one, L minus epsilon, and I make a band of width epsilon on each side, so it's total width 2 epsilon. And I have to find some number, oops, I didn't write this right. I'm getting the wrong definition here. I wanted the limit as x goes to infinity. I wrote the epsilon delta definition. My apologies. This definition is correct, but it's the wrong one I want to compare with this. For each epsilon greater than 0, there exists a number, let's call it n, like that one, such that absolute value of f of x, L minus f of x, is less than epsilon whenever f of x is greater than n. Then we say, and this was the definition I was supposed to put down, limit as x goes to infinity of f of x is equal to L. It's supposed to be a limit as x goes to infinity to compare with that one. I'm sorry. And so the idea is, you give me a number epsilon, no matter how small, I make an interval with 2 epsilon. And then I say, well, it looks like from here on out, if I call this n, from here on out, the function stays within this band of width epsilon on each side. That's what this is. This is the band of width epsilon on each side for the y coordinates, right? The y coordinate difference from L is no bigger than, is less than epsilon. So you have to be within epsilon, right? This little distance here at epsilon on each side of the proposed limit for y. So here's the line y equals L. And well, now you say, wait a minute, that epsilon was too big. I'll make my epsilon smaller. And so now you make epsilon this small, and you say, well, I'll just say, well, if I just go out to here, from hereafter, now I have a new value of n, and for this epsilon, I just have to start here. And then the function always stays within the band. And if no matter how small you make epsilon, I can always squeeze this one within the band just by starting far enough out, ever after keeping it within. Then we'll say the limit is L, because I can make this come arbitrarily close to the line y equals L just by starting far enough out. All right? That's how they made this concept rigorous in Calculus 1. For limits to infinity. The other one I wrote was for limit as x approaches the finite number. My apologies. So that's what you did in calculus 1. You squeezed it closer and closer. Now, how is this different here? It looks really similar, right? Starts off the same. There's just, for each epsilon greater than 0, there exists a number n such that f, instead of L minus f of x, it's L minus a of n, right? You can think of this as a function a of n, just a function of a natural number instead of a real number. And that's really the only difference, right? It's the same concept. And here's what's going on. You can think of this case as being just like what you did in calculus 1, except that the domain is only positive integers. The natural numbers, 1, 2, 3, 4, 5, and so on. And so you're only plotting a y value and a n value. This is n versus a n, if you like. You're only plotting a y value or an a n value for each natural number. And so you've got something like this. And if these natural numbers are settling closer and closer to the line y equals L, you tell me a bandwidth 2 epsilon, here's epsilon and here's epsilon. And if I just start far enough out, all the dots fall between these two. Then we say the limit is L. It's exactly the same thing. You just have to fit all the dots between the two dotted lines of width epsilon on each side of L instead of fitting the continuous function between the two lines. So it's actually just what you did in calculus 1. It's a nice, very similar definition, just for functions whose domain is the positive integers or natural numbers. Any questions on that so far? That's the concept. No matter how small an epsilon you pick, I can squeeze all the dots within a band of width 2 epsilon around epsilon on each side of L just by starting far enough out. Then we'll say the limit is L. Well, if you see this nice comparison, then you realize something immediately about proving limits. Wait a minute, if it's the definition is so similar, then maybe I can prove limits using exactly the same kind of theorems I did in calculus 1, right? By the way, if I forget to move that camera over, just get online or take your microphone off and wake me up. Once in a while, I forget to move it. There's these terrible stories of great mathematicians who got so concentrating that they forgot what they were doing. But when I see those, I feel better. I get concentrating and don't pay attention to the camera. So here's some theorems that have been proved using that definition. They're not so hard to prove, but we don't want to spend a whole lot of time on that. So theorems, if the limit as n goes to infinity of the nth term a n is L, we call that the limit of the sequence, is the limit of the a n's, is some number L, then we have the following results. One, what if you want to find, this first one, you don't actually need this hypothesis here, but what if you want to take the limit as n goes to infinity of a constant c? Doesn't depend on n, it's just the same number over and over. Like you have this list, 1, 1, 1, 1, 1, 1, 1. What's its limit? 1, obviously, right? Every number is 1. It's getting closer and closer to 1 because it's already there, right? So the limit of a constant is a constant, just like in calculus 1. You say limit of x is x. X. Limit of a constant is a constant when you have a continuous domain. Same thing when you have a discrete domain. So the limit of a constant is just a constant. And you just prove that directly from that. I mean, it's trivial. Let's just leave it off. If you take the limit as n goes to infinity of a constant times numbers a, n in a sequence, you can pull the constant out just like you could for limits in calculus 1. Isn't that great? It's not so hard, right? Because you already did this. So you can pull a constant out of a limit. And now we can add one more thing. Suppose also that the limit as n goes to infinity of another sequence with terms bn is some number L hat. if it has a finite number, limit, then we say that the limit is n goes to infinity of the sequence where each term is an plus bn is the same as the limit of the sequence with an's plus the limit of the sequence with bn's. Limit of the sum is the sum of the limits, just like in calculus 1. This is beautiful. The theorems are proved just basically the same way, just straight from the definition. And so this is L plus L hat, if you like. And same thing, if it's a difference here, then you just put a difference here. So those are the sum and difference rules. It's just like calculus 1. And you can do products and quotients, just the same also. Write those down real quick. So these all follow because the definitions are so similar, they're all proved similarly. Limit as goes to infinity, an times bn, when they both exist, is limit an times limit bn. N goes to infinity. And limit an over bn equals limit an over the limit, hope you can see this small, limit of bn. Limit of the quotient is the quotient of the limits, right? Just like in calculus 1. Better yet, suppose we want to prove something rather difficult, but we know how to do it similarly from calculus 1. I think this is the most fundamental thing of this section. Suppose that for all x greater than or equal to 1, f of x is defined this is a function of a continuous variable. When we don't say otherwise, x will always be a continuous variable, a real number, where n will n, k, k, l, m, n, p will all be integers. X and y and z will all be real numbers, unless we say otherwise. Suppose that for all x greater than or equal to 1, f of x is defined such that f of x is equal to a n when x equals n. You have a picture like this. You have a continuous function of x and y, and we can also call this the n-axis. And so we can look at discrete values, 1, 2, 3, 4, and so on. And we've got some sequence. Here's the ANs or the Ys plotted on this axis. And if the function is defined such that it interpolates these points, right? It's defined on x greater than or equal to 1. It goes through each of these, so f of x is equal to an at each point. So these are the dots are the ANs, and the green curve is the f of x. And suppose that the limit as x goes to infinity of f of x, the continuous function is L, then what would you think intuitively? The curve containing the dots is settling down closer and closer to the line y equals L. What must the dots be coming closer and closer to? Well, they're all on the curve, so they're forced arbitrarily close to the curve also. It looks intuitively, and it is true by this definition, that the limit of the sequence, limit as n goes to infinity of the nth term of the sequence, also called the limit of the sequence, is also the same number L. which means that you can apply all your theorems from calculus 1 to these, finding these limits of sequences, provided you just write a function that's equal to the one you see. Well, often you just do that just by replacing n with x and making the corresponding real valued function that way. So it's a very nice way to prove limits of sequences. For example, what if I ask you to find for this sequence, let's see, 2 over 4 3 over 5, 4 over 6, 5 over 7, and on forever. What's the limit of this sequence? Assuming I can glean from the information given that I have a pattern going, I say, well, this is the first term, A1, so I'll just label it 1. This is the second term. If you want, you can call it A1 instead of 1. This is the second term, n equals 2. Here's the third term, n equals 3. Here's the fourth one, n equals 4. Now, if you think about it, in each of these, the top is just 1 greater than the index. So this is 1 plus 1, 2 plus 1, 3 plus 1, 4 plus 1. So the top looks like it's n plus 1 for the nth term. Now the bottom, each one of these is 3 greater, right? 4 is 3 more than 1, 5 is 3 more than 2, 6 is 3 more than this one. So this looks like it's n plus 3. There's the nth term. If I say find the limit of this sequence, what I have to first do is figure out what the nth term is. The limit of the sequence is just the limit of the nth term. That's the definition. I didn't write it down formally, but limit of an is then the limit, n goes to infinity, of n plus 1 over n plus 3. And maybe you remember how to do these, I hope. If not, I'll make you. How do you find this limit? One way you did it in calculus 1 was you said, well, suppose I divide top and bottom by the highest power of n that I see. I can write this as limit n goes to infinity. If I divide the top and bottom by the same thing, it doesn't affect the quotient. So this could be 1 plus 1 over n, and this could be 1 plus 3 over n. Right? This is one way to do it. And now you recognize that as n gets larger and larger, 1 over n gets smaller and smaller. It's at 1, a half, a third, a fourth. This is being driven to 0. Remember, one of the theorems in calculus 1 was that the limit of 1 over x is 0 as x goes to infinity. That's also true for the limit 1 over n, because the limit 1 over x is 0, limit of 1 over n, a corresponding discrete function, also has limit 0. Similarly for 3 over n, it's 3 over 1, 3 over 2, 3 over 3, 3 over 4. Smaller and smaller terms being driven eventually to 0. So we'll say we know these limits are 0 because in calculus 1, their corresponding 1 over x and 3 over x functions have limit 0. Now that we know these are 0, this limit must just be 1 because it's being driven closer and closer to 1 over 1. So there's the limit of that one. You just pretend that it's x plus 1 over x plus 3 and do the same thing you did in calculus 1. There's nothing more to it than that. So a lot of sequences, the limit can be evaluated by that way. Just write the corresponding function of x instead of n and take its limit. And if it has a limit, then this one does too. Well, sometimes the numbers just get bigger and bigger without bound, or smaller and smaller with no lower bound. Oops, theorem. We'll say a definition then for take care of those cases of this. If the limit of n, as n goes to infinity of the nth term, the limit of the sequence, is a finite number, we say that the sequence A1, A2, A3 converges or is convergent. Otherwise, we say it diverges. So that'll define converge and diverge. It's just like calculus 1. Now, sometimes we want to be more specific, so maybe I should add one more thing to this, huh? If terms diverge, or the sequence diverges, get larger and larger without bound, we say the sequence diverges because it's not approaching a finite number. But in particular, it diverges to infinity. Or we can say the limit is infinity. And if it gets more and more negative without bound, negative numbers are smaller and smaller, right? So if they get smaller and smaller, meaning more and more negative, not closer to 0, without bound, we say the sequence diverges to minus infinity. And we write the limit of an as n goes to infinity is minus infinity. So that says for those kind of divergent sequences, sometimes we'll want to write this to indicate how they diverge. If they get bigger and bigger without bound, or more and more negative without bound. There's some other little theorems in here that I'm not sure they're all worth going through, but maybe you remember some other things from calculus 1. We can do theorems in analogy to the squeezing theorem or pinching theorem, you may have heard of called before. This again is intuitive. We won't go through the details of the proof. Instead, I'll just try to give you intuition for it. So this is the squeezing theorem or pinching theorem. If you have a sequence, maybe it's hard to find what the limit is, and your theorems there all fail to help you. Suppose that sequence, let's call it C1, C2, C3, and so forth, has for n sufficiently large, or we'll say larger than some number, capital N, the property that Cn is bigger than or equal to An and less than or equal to Bn, so that it's squeezed or pinched between the terms in two other sequences of ANs and BNs. And suppose also that the limit of the ANs as n goes to infinity is a number L, and the limit as n goes to infinity of the number Bn is equal to L. And this, I put L here, it can be any finite number, but it also works if it's infinity or minus infinity. So maybe I should put that here, L finite infinity or minus infinity. Normally when I write equals to L, it means a number, not infinity or minus infinity, but for this one theorem, we'll let it also denote infinity or minus infinity. If that's the case, then what do you expect? If you think about what this is trying to do visually, this is what it's doing. We put the picture over here. Again, if I plot n versus an, bn, or cn, whichever one you want to plot, the idea is that the ANs are settling down to some line y equals L because their limit is L. The BNs, oops, you should look right under these, are settling down to y equals L. Here's 1, 2, 3, 4, 5, 6, 7, 8. And the CN, suppose, are squeezed between them. So here's C1, C2, C3, C4. So they're always between those. Then what do you know? Well, these are squeezing them closer and closer to the white line y equals L. It follows that the limit as n goes to infinity of Cn is also L. That's the conclusion. You squeeze it between two convergent sequences, then it has the same limit. And if you squeeze it between two sequences that are going to infinity, then it's also infinity, or to minus infinity, it's also minus infinity. So there's another way to prove theorems. If you have a really difficult sequence that your theorems don't work for, maybe you can find some simpler sequences that you can squeeze it between and find out that what its limit is by squeezing it. Any questions on that? Let me know if I turn this too fast. Maybe sometimes you got to write something down. There are some other theorems here also. Maybe I'll just mention one more. It's not so important, but there's this one on even and odd terms that is occasionally useful. Let's add one more theorem to this. This is sort of intuitive too, I think. This is more for proving a limit doesn't exist, but it says if the limit of the ANs, limit of a sequence of ANs, exists and is equal to L, meaning it's approaching some finite number, then it's also true that the sequence of even terms is also has limit L, and the sequence of odd terms also has limit L. So if you take every other term, or then the limit is also L, and you can also take every third term will have to have the same limit, every nth term in general. So every even term, the sequence of even terms, and the sequence of odd terms have limit L also. So there's a whole bunch of those. Now let's try a few of these. problems here. Some of these are a little tricky, right? Once you get on the problem set. The example, we did a couple of simple examples. What is the limit? Oh, I need one more notation too. I'm sorry, I forgot to put it. Notation. This notation I've been using sometimes gets kind of long and awkward. If you want to write a sequence in brevity, sometimes we'll put this, parentheses AN, and we'll say that denotes the sequence A1, A2, A3, A4, and so on. Or sometimes we might put this, but then we don't save much writing, but parentheses AN, N equals 1 to infinity, or N equals infinity, right? Either way. This is notation for this. If you leave these off, 1 to infinity is assumed. If you want to start at some other number, then you have to put these on. So there's notation for the same thing that you'll see also in the back of the book. So let's try some sequences now. I had some ones here. I'll give you that notation. I said before, I'm not going to have you turn in the homework, but I'm going to assign homework every day. The object is for you to do it every problem and bring questions the next time as you're stuck. I really think you learn a lot more if you ask me questions. Sometimes I just don't realize what's hard anymore. You do enough of these. But then the problems on the test will be similar to the homework problems. I try and give you homework problems that are representative of exactly what I'm going to ask on the test. So that's the practice for the test, is to go through all the homework problems, make sure you do every one, then you'll get an A on the test, right? And what's more, I'll give you a practice test before every exam so that you can, try actually taking a test. It always helps to practice the ACT, even though you've already learned all the material, just to kind of feel the flavor of the test. So you'll be able to do all the homework tests. The practice tests will help, but they won't have everything on them. The homework list will have all the kinds of problems I might ask. But the homework will have all the things I might ask in the real test. That's the purpose of that one. Don't wait till the last second, right? You can sometimes cram at the last minute with history or social studies where you're just trying to collect a lot of facts. But mathematics, as you found in calculus 1 and 2, builds, and if you get a little behind, it's sure, all it's just like a bunch of Greek letters. It's sure hard to understand anything. Next lecture, if you skip a few, right? So, by the way, I don't know if I said this clearly at the beginning, but if you're not feeling well, don't come to class. You're not, or if you've been exposed to COVID, I won't, as I said, I don't require you to be here this semester, but at least watch online so you can pick up a lot of these tidbits as we go along. Like, how do you compare sizes of infinite sets? We'll talk more about that. It's very interesting, actually. Here's some examples then. Find the limit. Or say that they don't exist. Suppose I gave you this one. The sequence whose nth term is natural log of n. What's that? If you want, you can put on the n equals 1 to infinity, but that's assumed if you don't write it. How about, what's that one? Remember the big theme of this one? If you can just find a continuous function that at each n bigger than or equal to 1 is equal to this one, and it has a limit, then this one has the same limit, even if it's infinity or minus infinity. We'll say since the limit of the corresponding function from calculus 1, ln of x, as x goes to infinity, is what? Remember that one? So remember this, it's infinity. Or maybe I guess that was calculus 2, wasn't it? You can tell it from its graph, right? It goes up like this, and it gets higher and higher. It grows really slowly, actually. Y equals ln of x. But it gets bigger and bigger without bound. Eventually, this gets bigger than any number. So it does go to infinity. Since the limit of the continuous function ln of x is infinity, and it's equal to ln of n at each point, we'll say this is equal to infinity because the continuous function that interpolates it at each value of n has limit infinity. So that's how you can determine that one pretty easily. And most of these, if you just think, what if I replace n by x? What was the limit from calculus 1, right? Well, how about this one? B. Suppose I took the limit of, for this sequence, minus 1 to the n plus 1 over n squared. What's that limit? Well, you can kind of tell it by looking at it already. There's another theorem I wrote down in here that applies, but it's used so little I didn't bother to write it. But you could apply it directly on this one. That says if the absolute value of the terms of a sequence has limit 0, then the sequence itself has limit 0, right? If the absolute values get smaller and smaller towards 0.
Professor, the camera's not on the problem.
Oh yeah, I forgot to move it again there. Thank you. Oh, hate that. All right. So if the limit of the absolute values is 0, then the limit of the numbers themselves is also 0. So that's a theorem I left out, partly because we don't need it. We just simply say this. Limit as n goes to infinity of minus 1 to the n plus 1 over n squared, I'll say is hopefully the limit as x goes to infinity of minus 1. See, now this doesn't quite apply. I don't want to put the continuous function. I guess let's write it down just to say if the limit as n goes to infinity, this is the theorem I left out in there, of absolute value of an is 0, then the limit as n goes to infinity of an without the absolute value is also 0. And so let's look at this one, and we'll say since the limit of the absolute values as n goes to infinity, 1 over n squared is the absolute values, we can replace that with a continuous function. Limit n goes to infinity of 1 over x squared. And we know this limit, right? This one from calculus 1 is 0, right? Because these get bigger and bigger without bound. 1 over bigger and bigger numbers has limit 0. Therefore, this has limit 0 also because its absolute value limit is 0. So there's that one. How about this one? This is 17. I think some of these problems are on your homework, by the way. What is the limit as n goes to infinity of n plus 1, n plus 2 over n squared? This is going to improve your calculus 1 skills also. I always say that when I took calculus 1, I really honed my algebra skills. I became very good at algebra. I took calculus 2, I became very good at calculus 1. And calculus 3, good at calculus 2 and calculus 1. This will really make your calculus 1 and 2 skills better to take this class, because this is going to remind you, what is this limit? Well, provided it exists, we don't know that yet, it has to be the same as the limit as x goes to infinity of the same when we replace n by x, the continuous function. I didn't do that over here directly because minus 1 to the x plus 1, what happens when x is like a fraction? Then you've got a square root of negative 1. Like if you put minus 1 to the x plus 1 and x is a half, then you've got minus 1 to the 3/2 power. You've got a square, even root of a negative, and you've got to get complex numbers in there. So I did it this way instead. But on this one, we don't have to worry about it. There's not complex numbers. Let's see, I can't tell where that is. I think that's all right. All right. So now how do we evaluate this limit in calculus 1? We can say it's the limit as x goes to infinity and multiply out the top, x squared plus 3x plus 2, right? If I FOIL this times this plus this times this plus this times this plus this times this, gives me x squared plus 3x plus 2. You just FOIL it out. And now you say, what's the limit of that one? Use the same trick as before. Divide top and bottom by x squared. Rewrite this as the limit of 1 plus 3 over x plus 2 over x squared, all over 1. Divide top and bottom by x squared. These are the same quotient, right? Now, what's that limit? Well, remember, a number over x squared is driven to 0 as x goes to infinity. A number over x is driven to 0 as x goes to infinity. Theorems from calculus 1. So this limit is just 1 over 1 is 1. Because this limit exists, that means this one exists and it's the same number. So that's how we'll do most of those, is just do calculus 1 problems. Well, with that, it looks like I'm about out of time for tonight. Maybe that's a good stopping point. We'll just do 9.1. Try some of these. I did want to mention as we pass that actually you can do better than this. Instead of dividing every time, what you find out by dividing is that if you have a limit of polynomials like x cubed plus 3x squared plus x plus 2, and the power on the top is greater, what's going to happen? If you divide this through by x squared, you'll see you have limit of x plus 3 plus 1 over x plus 2 over 1 plus 1 over x plus 1 over x squared. And now the top is getting bigger and bigger on to infinity because of this x term, but the bottom is approaching 1. Now you recognize that the limit is infinity. So if the power of the top is higher than the power of the bottom, you simply say the limit is infinity. Instead of doing the division, you just say as soon as you see the power on the top is higher, you say the limit's infinity or minus infinity, depending on which, well, when x goes to infinity, it's infinity. If it's the same power, like this one, then you recognize when you divide through like this, it's just going to be the quotient leading coefficients. 3 over 1 is 3, right? Because once you divide through by x squared. Same as here, we get quotient leading coefficients, 1 over 1. And if the power on the bottom is bigger, then you divide through by x squared. You find the top becomes 1 over x plus 2 over x squared. And the bottom becomes 1 plus some stuff. The limit is 0. So if you want, instead of dividing, just say, well, the power on the top is bigger, so the limit's infinity. Powers are the same, so its limit is the leading coefficient quotient. Power on the bottom is greater, the limit is 0. And those 3 rules, maybe you remember those, apply to these quotients of polynomials like this. All right, let's try these homeworks for next time then. Again, they're not to turn in, but bring me questions on them. Out of 9.1, look at 1 to 29, all the odd problems. And if you do those, it won't be all Greek next time for the lecture. Come see me on Alice Smith Hours on WebEx if you get a chance. I'd love to get to see what you look like once in a while. And otherwise, I'll see you next time on Monday.
Thank you.
Yeah, thank you.